Okay, hey guys, this is my Lab 2 final presentation on distributed charge. So the introduction is going to be very similar to the last lab. We're going to use normal objects and the idea of charge to find the amount of excess charge on a piece of tape. And we're going to do this by observing the interactions of Scotch tape. And the fundamental principles involved here are Newton's second law, Coulomb's law, superposition, and we anticipate the charge to be between 1.6 times 10 to the negative 19th coulombs and 10 to the 5th coulombs. So the procedure for this lab is very similar to the last lab. Just to prepare a U-tape, we lay down a base tape and we adhere another piece of tape to it, and then we quickly separate those tapes, which creates a charge on the tape that we stripped off of the base tape. And then we're going to do this twice in order to create this bridge diagram. So here you see tape A and tape B, and they actually have like charges, so they end up repelling each other. And the idea is that we're going to use the electric force generated from the propulsion between tape A and B to make tape B levitate. So the idea is that F net is equal to 0 here. Gravitational and electric force will be equal to each other, so you can see that right here in that equation. And then the important part of this calculation, this is from the last lab where I used the point charge formula to find the electric force. The focus here is the charge that I calculated is 4.66 times 10 to the negative 9th coulombs, and this is going to be useful later on in the lab with one of the post-lab questions, so that's important to keep in mind. So here you can see part of my code, so I just went ahead and screenshotted parts of my code so it's easier to talk to through. So here the box that I've highlighted is the loop that calculates the electric field at each of the points, which is very important in this lab because it's distributed charge, so we'll be calculating the charge, we'll be calculating the electric field at different points along the tape. So in this case, we'll be calculating the electric field at 10 different points. And so this loop will return values, and then these values will then be plotted as arrows that are green, which you'll see on the diagram in a second. And then later on in the code, this is the calculation for the overall electric field. This will calculate the electric field of the top tape onto the bottom tape, and then the bottom tape onto the top tape. And then it's going to calculate the electric force at those points as well. Okay, and then this is going to plot the electric force and the gravitational force on the diagram, and then when you go to the code and you run it, you end up with this diagram right here. So if I go back and I choose to run this, you can see that you wind up with this diagram. So here, what you want to see is that the y components of the electric force here on these green arrows is going to sum up to the y component of this y arrow right here, which is the electric force, the total electric force. And the x components you'll see will cancel out. So this guy going this way will cancel out with this one going this way, and we'll end up with a net x component of 0, and we'll just have a y component of electric field, which will balance out the y component of the gravitational field we see here, which is represented by the yellow arrow. So here at the bottom, you can see that the magnitude of electric force calculated by the code is 1.962 times 10 to the negative third, and then the magnitude of the gravitational force is 1.962 times 10 to the negative third, which is ideal because we want these two forces to cancel out. So in order to get to this value, I had to modify my value of charge in the code, and I actually found that the value of charge in the code had to be higher than the one I calculated for the point charge for this to work as we wanted it to. So in the point charge question, I worked backwards from setting the gravitational and electric force together to find the charge, and in this case, I modified the charge to make sure those two forces would be equal as calculated by my code. So here in the post-lab questions, what if I modeled each of the tapes as a single point charge? Well, I would have gotten the Q value I got last time, which was 4.66 times 10 to the negative 9th coulombs. And the estimated value of charge that I got here is greater than the value I got when I did a point charge, and the estimates likely differ because in the point charge we're only considering the y component of that middle electric force, and we're not summing up the y components at various points along the piece of tape, and the tape has charge at more than just one point, so we need to really account for all of the magnitudes in the y direction of the y component of the electric field to get an accurate value for the overall electric force of the piece of tape. which means that this distributed charge equation is likely to produce a more accurate electric force than the other equation.